Dear students, welcome back. In this session, we will be learning about thermal energy radiations and how these radiations can be calculated in terms of power and its intensity. First of all, let us understand what is a black body. It says a black body is a perfect radiator of thermal energy. The emission spectrum of radiations from a black body is a continuous spectrum as shown. As you can see, the spectrum over here from a black body is continuous. It has all the colors, that is what they are trying to show. Consider this as a black body. Radiations are emitted from a black body, that is continuous emission spectrum. Now you can also see there is a specific graph which is shown over here, which explains the emission spectrum from a perfectly black body. On the y-axis it says spectral irradiance or intensity, you can name it as. On the x-axis it says wavelength. Now as we can see from the graph, let us understand the graph first, that this curve over here is different for a different temperature. For the temperature which is very high, the intensity is very high of the radiations, and for a temperature which is very low, the intensity of radiations is low. It also has some correspondence with wavelength. As we can see that if the temperature of the emitting black body is high, the intensity of this blue part of the visible spectrum will be high. And if the temperature is low, say for example over here 4000 K, then the maximum intensity will be of red color. So the intensity of a black body radiation depends on the temperature of the source or the black body while the time of radiations. Looking at the graph, let us understand these few points, important points from the graph. First is the maximum intensity is dependent on the intensity of the temperature of the source, this part. As we can see, the maximum intensity is depending on the initial temperature of the source. If the temperature of the source is high, the maximum intensity is high. Second part is, as the temperature is decreasing, the maximum intensity shifts towards the right. Higher temperature has a maximum intensity on the blue side of the spectrum, means the intensity bell-shaped curve is towards the left for higher temperature. This is what they are trying to say over here. Next part is, at higher temperature, the maximum intensity wavelengths are towards the blue zone of the visible spectrum. So as my temperature is increasing, my peak is towards the blue side. So the higher temperature, the maximum intensity wavelengths are towards the blue zone of the visible spectrum, is what they are trying to say over here. Next is, a body at room temperature emits infrared radiations but not visible light, so we can't see. Every body emits the radiations, but at room temperature they are infrared radiations, not the wavelengths are not within the visible spectrum, and hence we can't see. And the next part is Wein's displacement law. There is a law which is called the Wein's displacement law, which relates the wavelength with a maximum intensity with the temperature of the black body or any object which is radiating the radiations. And this law is given by this: T is equal to 2.9, which is a constant, into 2.9 into 10 to the power minus 3 divided by lambda max. Please make sure, it is very important that we understand, lambda max over here is not the maximum intensity, but it is the intensity at which it is the wavelength at which the intensity is maximum. It is not maximum wavelength, but the wavelength at which intensity is maximum. This is important to understand for the Wein's displacement law. Now there is another law which relates the parameters or the power which is radiated from the black body object. This law states that the power radiated or emitted from a black body is given by the following formula: P over A is equal to sigma T raised to the power 4. P is the power radiated, A is the surface area of the black body, sigma is known as Stefen Boltsman's law. It is there in the formula booklet for us. Its value is 5.67 into 10 to the power minus 8 over here, and T is the temperature of the black body, emission temperature of the black body. So the radiations, the power emitted depends upon the surface area of the object from which the radiations are happening and the temperature of the surface from which the emissions are happening. Now every object is not a black body, means it does not radiate 100%, it does not emit 100%. So to cater to that, we have another factor which says emissivity, and it is denoted by E. Formula for emissivity is E is equal to power emitted by an object divided by power emitted by similar black body. The word over here used is similar. We need to be very careful with similar. The meaning specified is any object which is at the same temperature and it has the same area. So emissivity, now catering to emissivity in the Stefen Boltzman's equation will give us the new equation which says P is equal to sigma A E T raised to the power 4, and the specific nomenclature is specified over here, where P is the power emitted, E is the emissivity, A is the area of the source, temperature of the source, and this is Stefen Boltzman constant. So this is the basic core concept which is related to the radiations which is emitted from a black body or any other body. To understand the similar concept when it is related to astrophysics, luminosity and apparent brightness of the star, please follow our next video.